Hi guys, welcome back. This video should hopefully be really short to make up for the other two long videos that we've had. Just remember, you can always pause a video. Pause it. If you're feeling tired, go have a nap, have some water, then come back and watch the rest of the video. Okay? Don't have to feel like you've got to watch the whole video all at once. Alright, so what are we doing now? Very short video. Identify fields as static or changing and as uniform or non-uniform. Okay, mainly this part here, that's what we're looking at in this video. So gravitational fields, uniform or non-uniform, what does that even mean? Well, let's first of all talk about uniform. So, uniform, I mean, if you think about what the word means, you wear a school uniform, all right, what does it mean to wear a school uniform? It means everyone wears the same thing, all right, and everyone's identical, almost. So a uniform field is a field in which the field lines or the gravitational field strength vectors are the same everywhere. Okay, then we call it uniform. One place that this can happen is on the local area of the surface of a planet. Okay, so you think how massive Earth is. Earth is just ginormous. But you just restrict yourself, say, to your backyard. Okay, maybe 10 by 10 meter backyard or something. It looks flat. Okay, you can't tell that the Earth is curved. It might be a bit bumpy here and there because there might be some more dirt in one area than the other. But overall, if you drop one object on one side of your backyard, it'll fall in the same direction as if you were to drop another object on the other side of your backyard. Okay, the directions of motion of those two objects as they fall would be parallel. What that tells you is that the force is pointing in parallel directions. So we're localizing our focus on a small patch of the surface of a very large object. Okay. Which can be approximated by a flat plane. And as we just said, you drop an object, both objects fall down in the same direction. Okay, so we say that the gravitational field is just downwards everywhere, right? Rather than say, here's a planet. I mean, yes, down, we sort of define down to be the direction an object falls. But in terms of these arrows, if you were to just localize yourself to your backyard, they'd all be pointing this way, okay? Because the ground is flat, right? And down is somewhere all the way out of the screen, all the way down there somewhere, okay? In fact, I'm going to show you a good Vsauce video that you can watch called Which Direction is Down. It's a really interesting video talking about why objects fall in the first place, sort of giving you an introduction to general relativity. Now, we've also got to talk about not being too far away from the object that's exerting the field. Okay, so we can't be too high up in the sky. Restrict yourself to a few thousand meters. All right, and then the strength of the field doesn't change. So the strength and the direction of the field has to be same in order for it to be uniform. Okay, so again, here's a picture. This is a classroom, right? The ground is flat. Down is the same in all directions. The arrows are all pointing in the same direction. They're all parallel because, you know, we're not going so far away from the surface of the planet. You only got the roof, which might be 3 meters tall. The value of G here is the same as the value of G here. It's the same as the value of G here and 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 everywhere. Okay? So the field strength is the same everywhere. The vectors point in the same directions. We say it's uniform. Okay? So we can approximate local areas as uniform fields. Again, now you're going to zoom out. We'll talk about non-uniform field again. All right, so here's the Earth. Zooming out, field points in different directions. So it actually is not uniform. It is pointing in different directions. The further away that you go, the weaker the field is going to get. However, just talking about the Earth itself, it's not a sphere. So we consider the surface to have a field strength of 9.8 everywhere. That's not true, okay? For the simple reason being that the Earth is not a uniform sphere. First of all, it's slightly squashed, as you can see with the distances that are written in this diagram. So the distance between the North Pole and the South Pole is actually slightly shorter than the distance from opposite sides of the equator. Okay, and it's due to the fact that the Earth is rotating and things like that. So it's not a sphere, it's an oblate spheroid. Oblate spheroid. Look it up, not making it up. And also the Earth's not uniform in density. Okay, there's more water on one side. There's probably, you know, more dense minerals in one portion of the Earth. So it's not uniformly dense. You're going to have variations of gravitational field strength all over the surface. And again, the video that I'm going to show you from Vsauce, they talk about this. Okay, so the center of mass of the Earth itself in the actual real physical world is probably not at the geometric center. Okay, it's probably off to the side somewhere, and it's probably always changing as well. Okay, because water's moving around. You know, the tectonic plates are shifting. It's always changing. Okay, so it's we call it a dynamic field, or a changing field. It doesn't stay the same all the time. It's not static. Okay, static means it stays the same all the time. That's it. That's pretty much it. All I wanted to say. Okay, we can consider a localized area of the Earth's surface as a uniform gravitational field, so we can simplify calculations. So if you can answer that question, that means you've understood what's going on in the video. All right, that's it. All right, I'll see you next time.